AirPods, so they're dying, and so I'm going to be using the microphone on my computer. So apologies if the audio is a little janky, but should be able to switch back over to the AirPods after a few minutes. Hopefully they get charged up enough that I can use them. All right, well, so let's get to it. So let me switch over to the Elgato. Here we go. Okay, so what we did last time, right, was we looked at Taylor polynomials, and we defined these things as being basically the question is, what are the coefficients, right? You want to build a polynomial. All you need to know is what degree is it going to be, and then what are the coefficients that it's going to be, okay? And what it turned out was that the coefficients were in terms of the derivative, okay? So the coefficient of the x to the n term depended on the nth derivative of the function. And that's still going to be true today, okay? So let's just say recap. Oh, I almost put a second P on recap. Thanks, Will. Yeah, recap. Oops, let me say it this way. Ah, damn it. Okay, so if we center our Taylor series, or polynomial rather, at the point A, then instead of having x to the n, we're going to have x minus a to the n. Everything's basically just shifted over. But the coefficient depends on two things. So this is this part right here. Is that better, Donovan?
Yeah.
Okay. Yeah. Is this better, Donovan? Okay, so the coefficient depends on two things, right? What degree term is it in front of? So n, okay? And then also it depends on where we're centering our Taylor series. So in many cases, A is 0 because the origin is a convenient place to center stuff. But it doesn't have to be. And but whatever point you're centering it at, that's the thing that you plug into your derivative, or second or third or fifth or whatever derivative, okay? So this stuff is still going to be true today, okay? So what's true today is, well, what's the difference between polynomial and series? Yeah, Kim? Well, but finitely many, right? Whereas a series could have infinitely many terms, right? So what we're going to look at is, did we look at any Mathematica with this last time? Did I plot some of these things? A little bit, okay. So let me actually pop back over to Mathematica for a second. And hang on just a second, you guys at home. Gotta switch the... I wish there was a way to auto-do this. Mathematica? Oh yeah, it's like 20 gigs. It's huge. Yeah, it's really big. I mean, but it's a super sophisticated piece of software that I use pretty much every day. So, I mean, I have a terabyte hard drive on this thing. So, believe me, I use quite a bit of it. Yeah, Kim? What do you mean? Oh, because Mathematica is superior. The series. So why not use a calculator? Well, I think the fundamental reason is everything a handheld graphing calculator could do, Mathematica can do 10 times better. Okay? And honestly, I think graphing calculators have outlived their usefulness for the most part for students. Now, if you're an engineer and you're going out in the field and you need something that you can carry in your pocket, then yeah, pocket calculator is great. But nowadays, everybody's carrying laptops around, right? When I was in school, I mean, I hate to be the back in my day kind of guy, but seriously, like when I was growing up, right, in the 90s, people weren't carrying around laptops. And if it was, it was business people, not like high schoolers. Okay, right? My computer was a giant box, and the monitor was also a giant box. We didn't have flat screens yet. I mean, this was the Stone Ages, gentlemen. And we had to use, when I first started using a computer, you know how I got to the internet? Through a telephone line. Yeah? Would dial up, would it be like, beep, 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 beep. Right? Did you catch that? Yeah, because they live out in the boonies. Right. So, anyway, but then, right, we all had graphing calculators, and I used it quite a bit. So I think really the fundamental difference between Mathematica and most graphing calculators, so there are two exceptions to this, the TI-89 and the TI-92 can do symbolic calculation, right? So if you ask the TI-89 or 92, what's the derivative of x squared, it will return the function 2x. Whereas if you graph, like on any other TI calculator, you graph x squared and you say, what's the derivative? It will give you a curve that looks like y equals 2x, but it's doing it numerically, not analytically. And that fundamentally is the difference between, Mathematica. Because like if I want to do, right, the derivative of x squared with respect to x, it's returning the function 2x, like analytically. It's doing everything the same way you would do on paper. That's why I like it better. Plus, we pay a lot of money for it, right? I think the license costs us between 25 and 30 grand a year. So damn it, we're going to get our money's worth. Okay. Anyway, okay, so let's do here. Let me take let's take the sine function as an example, okay? So actually, no, let's do, yeah, we didn't do the sine function last time. Okay, so there's the graph of sine. Oh, and let me make sure that everybody can see this online correctly. Yeah, okay, good. Right, there's the graph of sine from negative pi to pi. Okay, no big deal. All right, now what I'm going to do is I'm going to throw in here in orange. Well, let me actually do one other thing, just to make it a little easier to see. Thick, but it's CK, not THICC. Sorry. Yeah. Okay. So let me do one other thing here, and what I'm going to do is I'm going to throw in x, the function. Okay. And then the other thing I'm going to do is I'm going to say plot range negative pi to pi. So I'm going to make the y range the same as the x range. And then I'm going to make the aspect ratio 1 so that everything is correctly scaled. Right, so here y equals x genuinely looks like a 45-degree angle. Yeah, okay, just for the sake of the picture. Okay, so that's all I'm doing there. Okay, fine. So why did I do y equals x? Well, you guys can guess that that's the slope, or that's the tangent line at x equals 0, right? Because what's the derivative of sine? Cosine. What's cosine of 0? So the slope is 1. And what point do we go through? 0 comma sine of 0. Well, that's 0, 0, right? So we go through the origin slope 1. That's the tangent line. Okay, so this is T1 of x. All right, what about if we wanted to add on more terms to make this thing more accurate? Well, what we need to do is we need to know the other coefficients, okay? So what I'd like you guys to do is figure out what the coefficients of the x squared, x cubed, x to the fourth, and x to the fifth terms are. We're going to distribute this, okay? So, Lee, x squared term. Jack, x cubed term. Kim, x to the fourth term, x to the fifth, sixth, and seventh. Okay? Now, what do you need to do this? You need to know what the whatever derivative of the function is. Okay, so Donovan, sorry, you got to do the seventh derivative. Okay, but it's signed, right? So the seventh derivative is the same as the third derivative, right? Because it's a four-loop cycle. So the sixth one is the same as the second. No. Yeah, it's only because we're talking about sign. Yeah, okay. So give me those coefficients, right? And then I'm going to define a function that has the coefficients you guys give me. Okay, and I'm already going to put in, oops. Damn it, it would help if I could type today. Yeah, I'm really disappointed in what you can do and not do in Minecraft, by the way. Like, huh? Well, okay. But, well, we'll talk about that later. MAT112's great if you've got students who already know Java. Is my voice indecipherable, Coy? Let me get my AirPods back out. Hopefully they're charged up enough. Yeah, there we go. Huh? Okay. Is that better, Coy? My AirPods were near death, and so I had to charge them for a minute. Hopefully this is better. Yeah, so hopefully this is better, Coy. I forgot to charge my AirPods, and so after my first class, they were near death, and so I was using the computer's microphone to start. Okay, so those of you who are at home, you guys sort of check the coefficients and tell me if you agree with everybody. All right, so who had the x squared coefficient? Lee, what'd you get? Huh? And then plug 0 into that, right? Are we all clear on that? Okay, so what'd you get? 0. All right, now to be pedantic, I'm going to go ahead and write 0x squared. Okay, because I want you guys to notice something. All right, who had cube? Jack, was that you? What'd you get? No, that's right. Because it's 1 over 3 factorial, right? Well, here, let me just write it like this. Okay, so 1 over 6 x cubed. Kim, you had x to the fourth. What'd you get? Right? Okay, x to the fifth, Will? But positive, right? Okay, so what is 5 factorial? It's 120. Okay. X to the sixth term? 0. Donovan, x to the seventh term? Right. Okay. Now at this point, I don't know what. Right. So I'm just going to do that, and then it's x to the seventh. Okay. All right. So a couple things I want you guys to observe. What's happened to all the even terms? Yeah, all the even powers have coefficients of 0. And that makes sense because what kind of function is the sine function? It's an odd function, meaning that sine of minus x equals negative sine of x. If you have an odd function, then its polynomial will only have the odd powered terms. Similarly, if we did this for cosine, we would only have the even powered terms, and the coefficients for the odd powered terms would be 0. Okay, so I deliberately did that just so you guys would see the pattern. The other thing that you notice is we've only got the odd powers and they alternate, right? So every other odd power is plus and the every other is minus. And then the usual pattern, like we've got something over the factorial function. In this case, what are the values of the derivatives? They're either plus or minus 1, okay? Because what are we or 0. Because what are we plugging in? We're plugging 0 into either sine, cosine, minus sine, or minus cosine, right? And sine of 0 is 0. What's cosine of 0? 1. And what's negative cosine of 0, therefore, would be negative 1. Okay, so does the pattern make sense? Yeah? Okay. Now, if I graph this along with my function, sine, what do you guys notice? Pretty close. Okay, where does it finally look like where they're getting a little bit off of each other? Over at pi, right? Okay, so let me actually exaggerate this by say getting rid of the x to the 7th term. Okay, so I'm just gonna truncate it, right? So there, if I go up to x to the 5th, I get that, which is pretty good, except by the time you get over to pi, it's pretty terrible, right? And if I add in an x to the 7th term, well, it's a bit better. Not great, not terrible. But if I add that other stuff back in, it'd be that, okay? And because we know what the pattern is, what should be the next term? The next non-zero term, I should say. What would the next one be? 1 over factorial of 9, x to the 9th. And this one's going to be plus because the previous one was minus, right? And if I throw that in there, then you basically can't tell the difference between the polynomial and the function. Okay, so if I were to keep this game going all day long and build a series out of this, then the function would actually equal that series. Okay, so let's go back over to the iPad and write this out formally. Okay, so result, okay, and I'm going to use the dot 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 here, but we'll write this as a series like with a sigma in a minute. And hopefully Cole won't give me a B minus for the quality of my sigma. Huh? What do you think? A minus? Yeah. Okay. Man, it's a tough crowd. Mm-hmm. Did I screw something up?
I don't think I can stay in this room.
Um, are you currently having symptoms?
Maybe not.
Maybe not.
Yeah.
Did you get a green pass this morning?
Yeah.
Well, then you should be okay.
Oh.
Um, yeah. Okay. So, where were we? Sigma. Okay, we got the sigma. All right. Now, we need to be we need to notice a pattern. Okay, the first thing I notice is what kind of numbers appear? Only the odd ones. Okay, so I'm going to make my series start with n equals 0. Okay, therefore, what is the first term? Well, I'm going to have a -1 to the something, a something factorial, and an x to the something. Okay, and I'm going to fill in what those somethings are in a moment. Okay, but do you guys agree that it's going to be of that form? Why does it need to be x to the something? Well, we're building a power series. It's going to be something factorial, right? Because we saw that in our pattern. And then we need a -1 to the something because we noticed that every other term was plus or minus. Okay, good? Okay, so what we need here is a formula for an odd number. Okay, so what's a formula that always gives me an odd number? So let me say n and odd. So I want, when this is 0, to output 1 and so on. Okay, so give me a formula that would give me the output there, 1357. 2n plus 1. Okay, now does it make sense that 2n plus 1 is always an odd number? Because 2n is always an even number, and if you're one off of an even, excuse me, you're odd, right? Does that make sense? Okay, now, would 2n minus 1 have worked? Yes and no. 2n minus 1 is always an odd number, okay, for the same reason that 2n plus 1 is, but would 2n minus 1 have fit the pattern that I wanted here? Not in this case, okay? So do you guys agree that we need to use 2n plus 1 as our magic odd number generator? Yeah? Kim, you don't seem convinced. You are convinced? Okay. So what powers do I have? I have odd powers and I have odd factorials. Okay? All right, good. Okay, now what about the -1 to the something power? That's the last piece that we need to fill in. Well, when n equals 0, that corresponds to the x to the first term, right? Because of our 2n plus 1 formula. Okay, so when n equals 0, that's the, so let me write up here n 0, 1, 2, 3, 4, etc. Okay, so what do you notice about who's odd and who's even given n? Which terms are odd? Or sorry, sorry, I didn't mean to say odd or even. I meant plus or minus. Which terms have pluses in front? X, x to the fifth, and then the next one would be x to the ninth. What's true about the n for those values? They're all the even numbers. Okay, what about the odd ones? They're all minus. So if I do -1 to the n, well, if n is an even number, then what's -1 to an even power? +1. What's -1 to an odd power? -1. Okay, so does the pattern fit? Yes? Okay, Gucci. So this is the Maclaurin series. Oops. For sine of x. Okay. Why is it a Maclaurin series as opposed to a Taylor series? So what's the difference between them? A Maclaurin series is always what, Jack? Centered at 0. A Taylor series is what we call it if it's centered anywhere else. Okay. But you guys can see for convenience, often we'll center it at 0. Now, I will probably slip and say Taylor series, even if it's centered at 0, but, right. Oh, it's more complicated than that. Taylor didn't come up with Taylor series. Actually, Kramer did. But Taylor came up with the thing that's now known as Kramer's rule. So it's all, they got even. Well, I mean, it's kind of like we talked about L'Hopital's rule, right? L'Hopital didn't come up with that. The only reason it's named after him is because he put it in his calculus book. And, but he had basically one of the Bernoulli brothers on retainer to like write letters to him about calculus or math that he was learning and figuring out. And then L'Hopital made a calculus textbook, and everybody learned out of that textbook, and so that this came to be known as L'Hopital's rule because it was in his book. So anyway, okay, so that's the Maclaurin series for sine. All right, now what I'd like you guys to do is, what's the radius of convergence? You're going to have to do what now? What are you going to use to do this? Will? Mm-hmm. Okay. So you're going to use the ratio test, right? Let me give you a hint. The test you need to do rhymes with Schmatio test. Okay. So let's do the ratio test to determine whether or not when this thing converges. Okay. So what I have to do is I need to look at the limit as n goes to infinity of a sub n plus 1 divided by a sub n Kim, did they tell you to? No. 2n plus 3? Well, okay, so let's think about it. If I plug n plus 1 in for n inside the formula 2n plus 1, well, then I really have 2 times parentheses n plus 1 plus 1. Well, when I distribute everything and collect, what do I get? 2n plus 3. So that's why it's 2n plus 3 on the first thing, because I've replaced n with n plus 1, but that makes 2n plus 1 turn into 2n plus 3. Okay, are we clear on that? Oh yeah, you're right. Although it's not actually going to matter because of the absolute value, but yeah. Okay. So here I wrote the -1 to the whatever terms. I could have just not worried about that because I've got the absolute value anyway, so they're going to disappear. But just for sake of completeness, we'll do that. Okay, now that I've got all that, let's crunch through the algebra here. Right, so a bunch of stuff's going to cancel. First off, I don't need to worry about the -1 to the whatevers anymore because of the absolute value. But then what is 2n plus 3 factorial? Well, it's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. We've got a 2n plus 1 factorial up on the top. Okay, so scribble that down, make sure you're Gucci with what we've got so far. Okay, so we cool with the simplification up to here? No. Okay, so then the 2n plus 1 factorials cancel. That's nice. So this and this go away. And all we're doing now is taking the limit of that. Okay, what is the value of that limit? And remember, it's n going to infinity, not x. X is a constant as far as we're concerned. Donovan, pop quiz. What's the value of that limit? Big time, 0. Regardless of x. Okay, so in this case, the value of that limit is 0 no matter what x is. Okay, which means what's the radius of convergence? And what's the interval of convergence? Jack, pick one, radius or interval. Your choice. Huh? Okay, that's fine. Take another minute. I know I'm putting you guys on the spot. I can get my phone to stop blowing up. Of course, half of it's junk. Can you guys believe we're 70% through the semester without finals? I know, right? Yeah, basically.
Do you know when our finals gonna be in here?
I'd have to look at the. No, no, I don't remember off the top of my head. It's whatever. Whenever the registrar says it is.
So everybody kind of has like their day to do it.
Right. So each class slot, like all classes that meet at 9:05 on Monday, Wednesday, Friday, have their final at the same time, right? And they're the registrar basically just makes up a schedule, and that's what you do. And then if you've got a class that like has a final paper instead, well, then you don't have a final per se, but yeah. So I don't remember off the top of my head which slot we're assigned to, but it's I can show you after class where to look that up. It's real easy. Okay, just go to the registrar's website basically, and but I'll show you there. All right, Jack, did you figure it out? It should always converge, which what does that mean about the interval and the radius? Right? It's the entire real line, and the radius, in that case, we say is infinity. Okay. Um, Now, in this case, do we have to worry about the endpoints? Because they don't exist, right? Negative infinity and positive infinity aren't numbers, so I can't plug those things in. Okay, so this thing super converges, and what we would see if we went back to Mathematica is the more and more terms you add, the further away from 0 the convergence looks good. Okay, all right, now, could we play the same trick with cosine instead of sine? Yeah, okay. So here's what you would end up getting. And should that come as a shock? Okay, so why is that maybe not surprising that that's the form for cosine? Yeah, they have similar traits. The only real difference here is what do we have? I've got even things instead of odd things, but it still alternates. Okay. Um, Now, here's another way I could actually prove that this is true. For example, well, isn't cosine the derivative of sine? Yeah, okay. What's the derivative of a sum? It's the sum of the derivatives. The power rule says the power comes down. You take one away from the power, and then if we simplify, we get that, right? Because the 2n plus 1 cancels with the 2n plus 1 that's in the 2n plus 1 factorial, leaving a 2n factorial in the denominator. And lo and behold, that's exactly the series that I claimed for cosine. Okay, does that make sense? Okay, so what's the series for e to the x? Oops. It's this, x to the n over n factorial. And we kind of saw that last time because what was the sort of the Taylor polynomial that we were cooking up? We cooked it up for e to the x. And what did we keep noticing? What was the derivative at 0? It was 1 every time. And so our coefficients were just 1 over n factorial. Okay, does that kind of make sense? Yeah? Okay. Um, so how would I build other Taylor series knowing these? Okay, so for example, how would I build a Taylor series, say, for x squared, sine of x squared, excuse me? Well, do I know a Taylor series for sine of x? Could I replace the x squared with, replace the x with x squared? Yeah. Okay, so let's do that and see what we get. Ah, sorry. Okay, at this point, what I'd probably do is say, break it up and write it like so. I'd probably write it as -1 to the n, 2 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. Oh, I'm sorry. Thank you, Will. God, they'll just tire anybody to teach around here. Oh, sorry. Thank you. There. Okay. So, yeah, so you can just replace x with a formula and then you just do it and then see what you get after you simplify. Okay, Now, why is this really handy to have a Taylor series for, say, sine of x squared or some other random thing? Well, what about if I wanted to do the following? Do we know how to do that antiderivative? If it were sine of x, we'd be Gucci, but it ain't. And it's not x sine of x or some sine, x sine of x squared. So I can't do like u substitution. Trig substitution ain't going to help here. In fact, no technique would do this. This is a special function, okay? But could I at least get a series answer for the question? Yeah, because what could I do? Well, if I know the series for sine of x squared, how do I get a series for the integral of that? Well, what really is a series? It's a bunch of stuff added together, right? So if I gave you two functions f and g, and I asked you to tell me the integral of f plus g, what would you do? You'd do the integral of f, you'd do the integral of g, and then you'd add the answers. Well, does it matter how many things I ask you to add together? What about if I ask you to add up infinitely many things? Is the integral of a sum of infinitely many things the sum of the integral of all those things? Yes, trust me, I'm a doctor. Okay, you can do that. Okay, so could I just integrate this thing term by term the same way that I differentiated sine earlier to get cosine? Totes. Okay, what's the one thing you have to worry about though if you're doing an antiderivative? The plus c. Okay, so if you integrate, right, you get that pesky plus c. Yes? Well, how do we figure out what plus c is? Well, do you know what the sine function, what is it if you plug 0 into it? 0 in this case, right? And that allows you to, knowing a point that the function goes through allows you to figure out the constant. Okay, in this case, it would end up being 0. Okay. Okay, so you could do that by integrating term by term. All right, so now let me show you guys something really cool. First off, let me just copy these two formulas down for reference sake. Okay, so there's sine and cosine's Taylor series or Maclaurin series. Okay, I give you the following quest. Find me a Taylor series for tangent of x. What's one way to do it? Yeah? Kim? Do the division, right? That's one way. The other way is to say, oh, well, tangent is the function, so I need to start looking at the derivatives of tangent. What's the first derivative of tangent? Secant squared. Okay, well, what's the derivative of that? 2 times secant times tangent because of the chain rule. And then what's the derivative of that? Well, now I've got to use the product rule also, and it's going to turn into a giant mess. Okay? Or we could turn it into the following giant mess. Okay, so, oh, do I love this. Okay, what's it look like I'm about to do? I'm going to do some division. Well, it's not synthetic because I'm not dividing by a linear factor, but yeah, you guys remember doing long division back in school? Well, like back in High school, middle school, elementary school,
College school.
college school, yeah. Okay, so we can do long division, right? So in elementary school, you guys learned how to do long division of numbers. And then in, well, 4 of you high school, 2 of you middle school, learned how to do long division with polynomials. Yeah?
I walked in the class after two, and they just learned, like, I was at Dr. Clement, they just done the long division. And then he's like, yeah, which can use the other method.
Yeah, but that only works if you're dividing by only a linear factor. Otherwise, you can't do it. Okay. Well, I've got good news for you. What's the algorithm? It's exactly the same as the algorithm for doing it with numbers back in grade school. The only thing you have to be careful with is the bookkeeping to keep all the stuff organized. Okay. So, how many times does 1 go into x? X times. Okay, so what do I have to do? Multiply. Okay, so that would give me x minus x cubed over 2 factorial. Okay. Okay, so what did I do? I multiplied x by everybody in my divisor and was very careful to keep everything in line. And then I need to subtract all of that from my dividend. Okay, now the first term is easy. X minus x is 0. That's good. But what am I going to have to do for the rest of it? Fraction foo. Okay, because what do I have? I've got minus a sixth plus a half is what? 2/6 or 1/3. Okay. All right, what's the next term? Well, what's 1 over 120 minus 1 over 24? 1 over 120 minus 1 over 24. Well, what's the common denominator here?
Oh, it would be 24 times 5.
Right. So it'd be 1 over 120 minus 5 over 120. So negative 4 over 120.
So negative
1 over 30. Oh, it is delightful. Okay. Well, all right. So we're technically never finished with this, but um, what would be the next step? Repeat, right? So how many times does 1 go into 1/3 x cubed? 1/3 x cubed times, right? Okay. And is it going to be plus or minus? It'll be plus here. Okay. And then I multiply and do this all over again. All right. So I get 1/3 x cubed minus 1/6 x to the 5th. The next term would be plus 1, what's 24 times 3? 60, 72? Yeah, okay. 1/72 x to the 7th, and so on. Then what do I have to do? Subtract. Okay, so what's 1/30th plus 1/6? So that's 1/30th, or sorry, minus a 30th. So it'd be plus 5/30ths, so that'd be 4/30ths or 2/15ths. Yep. Okay, and plus, right? So I'd have 2/15ths x to the 5th, and so on. All right, so what's my next term going to be? here 2/15. Okay, do we get the idea? This is a giant mess, but it's a good giant mess. It's a fun giant mess. Now let's check our work and make sure we didn't screw this up. Watch this. Huh? Oh, because the divisor, the cosine series, is um, that's just what the cosine series was, right? All right, so let's just make sure I didn't screw this up and then we'll quit. Hold on, let me make sure I remember. Oh, 0 comes next, yes. Huh, looks like we nailed it, right? Uh, the next term that I've omitted, of course, there'd be something to the 7th term. And if I wanted to go out and find out what the next one would be, well, let's just go out 10 terms and see what we get. Yeah, gets kind of messy. But let me truncate the terms and let me plot it. Hey, that kind of looks like tangent. Yeah, yeah. So infinite polynomial foiling or long division is totally a thing. Isn't this fun? Yeah. Oh. Well, it's another way to get a series for tangent, right? So anyway. All right, we should quit because Pofald's invading. All right, see you guys next time.